So in this video I want to talk a little bit about the idea of electric potential. Alright, and to talk about electric potential we need to deal with electric potential energy. Alright, so it comes from that idea. It's not quite the same thing. Electric potential energy is just going to be the amount of energy that we have stored in something due to its electrical charge. So let's take a look at an example here. Let's say we have a positive charge right here. Alright, let's say it's stuck. Alright, we'll stick it down here so it can't go anywhere. And if I have say I have a negative charge then over here somewhere, right? We know that opposite charges are going to attract, right? There's a force of attraction here that pulls between the two of them, right? Both cases. So this one's stuck, it's not going to go anywhere, but this charge right here, this negative charge then is going to move, right? You have some velocity and head over towards it, and eventually it's going to just, let's get that out of the way. Right, eventually then it's going to be right here. Alright, it'll be stuck to it, and so now it's not going to go anywhere else. It's just, you know, in this little place right here. So we can look at that situation and say, you know, there's really no potential here to do anything. So we can have an electric potential energy of 0. Alright, so we'll just call that PE with little e from now. So that's our electric potential energy. In this case, there's none. It doesn't have any potential to do anything, any change whatsoever. Opposites attract. They want to be stuck right next to each other. Now, if we kind of take a look then at this situation here, we started with the charge right there. In order to move this charge, I need to apply a force. Right? So maybe I pull this. Right? I'm able to grab a hold of this charge and pull it. I got a force that I'm going to pull with this and drag this negative charge back out across, and I can drag it back out over here. All right? When I do that, you know, it moves a distance, right, in that same direction. So by applying this force of pulling it to it here, I've applied a force over a distance, and that's just work. Work is force times distance. So I've done work to this charge, this negative charge right here. And in doing work to it, I have transferred energy to it. And so now out here, because of that work that I did, there's some potential energy, electrical potential energy that this particle has. When I let go of it, it'll head on back towards that positive charge. It has the potential to be attracted to the positive charge. So that's kind of the idea of electric potential energy. And this is very much like we talked about with gravitation, in that the particles are attracted to each other. Let's say we look at the situation where we have a positive charge. And it's still stuck, right? We don't want this one going anywhere. I'm just going to look at what happens. And let's say I have another positive charge out here. So what happens? Well, we know the forces that are going to be applied are repulsive forces. So there'll be a force pushing this one and be a force pushing that one, but we don't actually have any movement here because it's stuck, right? So this one here is going to have force. It's going to take off in that direction, right? It has the potential to move farther away from this. So there's some potential energy here in this case, some electrical potential energy. And so you can push off, just go on past the screen what I can even see. But let's look at the situation similar to what we just did with the negative charge now. Let's have me come in here and apply a force to it. I'm going to push, so I push on this positive charge, and I push it against this repulsive force of the other positive charge. As a result, eventually we get the positive charge in here right up next to the other positive charge. All right, now in this case, you have, again, we've applied a force over a distance. You have it, in this case though, you have a maximum, the maximum electric potential energy you're going to get. Because you've got them as close together as you can, and so as soon as you let go of it, then this positive charge is going to take off again, all right, away from, so it has that potential in that case. and it'll go farther away and you'll have some potential energy. At some point out here you probably have a negligible amount of potential energy, but you don't really technically have zero potential energy in this case, because it just is going to keep getting farther and farther and farther away in that situation. So the idea of electric potential energy, right, the idea of the electric potential energy here, right, is just that stored energy. So again, just like potential, we talked about it before, stored energy due to the relative position of charges, or say due to the position of a charge in an electric field. Right? So, as we looked at before, each of these charges, particles, have electric fields, and so just like gravitational potential energy, you have that stored energy due to position. This is stored energy due to the position within that actual electrical field. The potential energy is one thing, but in electricity we're concerned about the actual amount of electric potential energy that we have per the amount of charge. So remember, our Q stands for the charge. How many coulombs, right? How many coulombs of charge do we have? So we're looking at that idea. And this is the idea of electric potential. So the electric potential is basically saying, okay, sure, I've got, so many joules of energy stored here, but how much energy do I have per charge? It's like, you want to look at the individual charges or the individual electrons maybe. Each individual electron has a certain charge, and then we're concerned with then, well, how much energy does that have as well? So how much energy, potential energy, and how much charge do we have there? That ratio, right, potential energy per charge, is the electric potential. Now, potential energy is measured in joules, and charge is measured in coulombs. So a joule per coulomb is the unit for electric potential, and this is what's known as a volt. You may have heard about that, and the idea of voltage. And so electric potential is very much related to voltage, but it's not exactly the same thing. Voltage is actually just a change in the electric potential. We'll look at more detail with that when we talk about electric current and everything. But for right now, we'll look at the idea of electric potential. We can kind of refer to it as voltage. It commonly is, but it is measured and recorded in the idea of volts. So let's try a sample problem. So you may recall I took the balloon in class and rubbed it on my sleeve and everything. The idea was to charge up the balloon specifically, and we know we charge the shirt as well. So the idea was you took some negative charges, right, that were here, rubbed them off onto the balloon, and we got a negatively charged balloon. So let's say in that process of doing that, so let's say I did about 2.2 joules of work in moving those electrons over, right? And let's say I moved 0.00055 coulombs of charge with those electrons. All right, so I'm not so much worried about how many electrons, but the charge associated with that. So my question then here would be, what's the electric potential then? What's the electric potential of the balloon, all right, as a result of this? What's the electric potential of this potential energy now that's stored with that charge on the balloon and the amount of charge here? So my electric potential, all right, just an abbreviate this, my electric potential is equal to that potential energy, right, my electric potential energy, and so that's the same as the amount of work that I did. So I have 2.2 joules divided by, and there's my charge, 0.0055 coulombs, right? 3 zeros, coulombs. And so then that's going to give me an electric potential of about 4,000 joules per coulomb, or is commonly referred to in the units of 4,000 volts, right? So we might call that as a voltage, right, electric potential, more properly, of 4,000 volts, right? So now that sounds like a lot. We think in terms of volts, we think of high voltage and electricity. But again, look at it. It's only 2.2 joules. That's not a lot of energy. And energy is what causes the change. So the fact that we have a large electric potential is not so much the important part here. It's really how much charge do we actually have. So we have 4,000 joules per coulomb, but we don't have a whole coulomb. Right? We have a very tiny fraction of a coulomb. And in most situations, when you're dealing with electrostatics and you have charge transfers and things going on, you're talking about very small charges that have been moved around there. So you have very little energy in the system, and the energy total is what's really going to cause, the damage, the pain, things like that. When we start talking about current electricity, you have 4,000 joules per coulomb. In current electricity, the charges just keep flowing, and every coulomb that comes through carries 4,000 joules of energy. And so you talk about high voltages of 500,000 volts, that's 500,000 joules for every coulomb. So it gets to be a big deal there. But in basic little electrostatics and things like that, it's really not a major issue. So we have our balloon that we were charging up in class of about 4,000 volts.